Okay, so it's a great pleasure to introduce Winston Heap, a great friend. And Winston is going to talk about main values of long Dirichlet polynomials. So Winston, you can start.
Okay. Well, thank you. Thanks for the invitation as well. You got a very nice seminar series here for sure. Yeah, so I want to talk about mean values of long Dirichlet polynomials, and I'll talk fairly generally initially, and then we'll look at Dirichlet polynomials over primes, do some survey stuff on some applications of that stuff in zeta function theory, and then hopefully I'll be able to talk about some new results towards the end. So let's just look at the general case first. So you want to look at mean values of some guy that looks like this, mean square really. And why might you want to do that? Well, the reason is that these Dirichlet polynomials provide approximations to L functions in regions where the Dirichlet series doesn't converge. So like on the half line or something like this in the region of analytic continuation. And the key feature about these approximations to these L functions is that the further you go up the critical strip, the more terms you need to take in this partial sum here in order to keep the approximation alive. So, you know, what happens is when you're at height, say t, the length of this sum here is going to depend on t. And this provides some sort of problems for computing the mean square of these things. But, we'll get to that in a second. Okay, so I've got like a couple of examples here. So the kth power of zeta is given by this sum involving d sub k here. And as I mentioned, the key feature is that the length depends on t. So if you're at large height t, you have a sum of length t to the k over 2 here. And these, this approximation here is accurate pretty much point-wise. I mean, you have a conjugate sort of dual term plus some small errors, but point-wise, this is pretty much accurate here. And here's an example involving what will be important for us: Dirichlet polynomials over primes. This is for the log of zeta. You can approximate this by some guy that's of length some small power of t here. And this approximation here needs to be taken like a little bit more liberally. It's not point-wise, this is more just like on average, say L2 sense. Okay. So we want to compute these mean values, some large height t, mean square. And so the general problem is thus, so you have some coefficients satisfy some sort of divisor bound, and the length of the sum here is going to be dependent on t. And I think the simplest way to explain what's going on with these types of mean values is, well, just to state a theorem. And in this case, we have essentially an approximate Parseval identity here in a sharp form due to Montgomery and Vaughan. Okay, so on the right, you get the length of the integral t times the mean square of the coefficients here plus some error term. And you'll notice that in particular, if the length of the sum n is little o of t, then we're getting an asymptotic formula, right? Let me shift this. If n is bigger than t, however, you lose the asymptotic and you just get an upper bound. Now this is a result for general Dirichlet polynomials, and in some cases it's sharp, but in a lot of cases where we can actually compute this mean value for n larger than t, say t to the 3 over 2 or t squared or something, well, you can do that for, say, like the constant function. In these cases, this upper bound of n times this is quite far off, because you actually get something that's just a constant c times the t here. So yeah, for the cases that we're interested in, this upper bound is really really far off, basically. And so when you have a long sum, you need to do much more. So just to set some terminology, if n is, well, let's say little o of t, then you call it short Dirichlet polynomial, and if n is bigger than t, then you've got a long guy. So for short guys, we understand them pretty much as you want. You have a asymptotic and essentially pure orthogonality. For long guys, well, we don't really understand them at all, except in very specific cases. So I want to talk about these guys, obviously. And let me see, like, what do you actually do if you have a long guy? Well, you do sort of the natural thing, right? Just to expand the mean square, push the integral through, and then you can take diagonals, m equals n. This gives you this term here. And for your off diagonals, you just integrate directly to give this guy here. Now, for your diagonal terms, you have no oscillation, so you get a large term here, large contribution. For your off diagonals, you do have some oscillation, but you have a lot of terms, right? I mean, almost all of the terms in the double sum are living here. So there's a lot of terms to deal with. Another thing to note is that actually, if this ratio, okay, it might not be equal to 1 for the off diagonals, but it can be really close to 1, especially if n is large, right? And in that case, if this ratio is really close to 1, then you have quite little oscillation, and your integral can actually start to look of size t here, or start to give a good, decent sized contribution. And this is sort of reflected in this log in the denominator here, which blows up when m gets close to n. Okay. So for long guys, there's quite a lot to manage. There's a lot of terms, and some of them can actually get a reasonable size. What ends up saving you in the cases that we know is the fact that you have cancellation amongst the off diagonals for different ratios here. Yeah, so that's what ends up saving you in the end. And to sort of, so the next step, if you want to kind of try and exploit that cancellation, well, you can write, so you can partition the off diagonals where you have a fixed difference between m and n. And in that case, we can understand this ratio here. So if you do that, so write m minus n equals h for some h, fixed h, and then average over h. Well, when you do that, it's quite clear that you need to understand these correlation sums here. And of course, we started with an L function, right? So multiplicative coefficients. And so now you get this very tricky problem where you have an additive shift of some multiplicative coefficients. So these sums are quite hard to understand in general. And in order to exploit this cancellation that I mentioned, you need to understand these guys like really well. So typically you'll need like a full asymptotic formula for this with a power saving in the error term, if you want to do anything. Upper bounds aren't really sufficient. You just get a really bad bound for your off diagonals. Okay, so we have this is the problem that you need to understand if you want to do these long guys, right? So let's have a look at a few cases where this stuff is actually known. Of course, the constant function is doable. There is some multiplicative functions where it is doable. So namely the divisor function is actually doable. In the case k equals 2, just the usual divisor function. So this is nice. It has some nice properties. In particular, you can unfold the divisor function, and then you're just counting solutions to linear Diophantine equations, which is doable, right? So in the case of divisor function, the sort of state of affairs is, say, some full asymptotic formula. We do have that with some power saving in the error term, and there's quite a few contributors to this sort of stuff. This is not an exhaustive list by any means, but I'll just mention that so the current best is this error term here is theta is 2/3, and with some decent amount of uniformity in the parameter h. And as you can see from this sort of stuff, there's quite a bit of heavy machinery going in. It's like the usual culprits of like analytic number theory. You have either Wales bound, so RH for curves over finite fields, so there's stuff coming from algebraic geometry, or you have these Kuznetsov formulas for sums of Kloosterman sums. So yeah, the usual culprits of like heavy machinery in analytic number theory go into this, and this is the sort of best stuff you can get at the moment. Okay, so that's the case k equals 2 for the divisor function. For k bigger than 3, bigger than or equal to 3, it's quite mysterious. We don't really know anything in terms of precise asymptotics. So it's conjectured that you have some asymptotic formula of this form here, where you have a polynomial in log x of this degree here. And I should mention briefly, why would you expect this to be the degree here? Well, d sub k is log x to the k minus 1 on average. And so what this is saying is that these two guys are acting independently, which you probably expect, right? Because you have some additive shift. I wouldn't expect the multiplicative structure of n plus h to be related to that of n, you know. Okay. So as I said, in terms of asymptotics, this is just a conjecture. There do exist some results on average over h. But unfortunately, the error terms aren't quite as strong as this in the general case. And it's unfortunately not enough to give new results for the 2kth moment of zeta, for example. And just to sort of put these ideas in context, let's say you wanted to compute the 6th moment of zeta, and using some sort of formula like this. Well, for the 6th moment, you have sums of length t to the 3 over 2. And as it happens, you can just average h over such a length here. Now, for the 6th moment of zeta, you're expecting something of size t times log t to the 9. And when you do the off-diagonal calculations, the error term here translates directly into the error term for the 2kth moment of zeta, once you input the length here. So in order for that error term to be less than t log t to the 9, say less than t, or little o of t, you would require something of this sort of order here. So theta less than 2/3, since we have a sum of this length here. And of course, with some uniformity in h. I mean, given that this is the current best for the divisor function, the usual divisor function, it seems quite far out of reach at the moment. Yeah, the situation gets like even worse when you look at higher moments. So for example, for the 8th moment, you have sums of length t squared. So in this formula here, you'd require theta equals a half, which is square root cancellation and no plus epsilons in the exponent. That would just ruin everything. So yeah, it's really asking for a lot. It seems a little bit too much. And of course, for higher moments still, you would require pointwise better bound and square root cancellation. It's just not going to happen, right? So for higher moments, what's expected is that when you average over h, these error terms here exhibit some cancellation amongst themselves as well. So it's kind of a very, very sad situation. We don't really know what's going on here. I bet there's some big expectations for this type of behavior. Okay. So I go over the divisor function because it's like a good example, I think, to show what you sort of need for these long guys. The majority of the talk, as I mentioned, is going to be about primes. And in this case, the situation is like equally sad, if not more, because the correlation sums that you need in this case are essentially versions of the twin prime conjecture. So more specifically, it's the Hardy-Littlewood K-tuples conjecture. And this predicts something of this shape for some constant G of H here. Okay. So again, for this guy, there exists some results on average over H, but we don't know. So you get like a result, an asymptotic for almost all H, but we don't know which ones, obviously. But yeah, aside from that, obviously this conjecture. So I'm going to look at some, as I mentioned, I'm going to survey some stuff on zeta function theory where you use primes and where this type of conjecture might crop up. So that's the sort of general case, and let's look a little more specifically at some examples in zeta function theory. Okie doke. So any questions at this point?
Yep. Hi, Wayne. I have a question. When you spoke about the correlations of the divisor function, right?
Mm.
Do you know how is dependence in H?
What, for this guy here?
Oh, yes, no, for k equals to 2, the previous slide.
Hmm.
Yes, that constancy 2.
Yeah, it's like it's a divisor function. It's a divisor function, but you weight the divisors with 1/d. It's like this sigma minus 1 function.
Okay, thanks.
Yeah, and there's like a zeta 2 constant. Okie doke. So the first thing I want to look at is Montgomery's stuff on pair correlation of zeros. And so here we're looking at how zeros at some large height interact with each other. So how close can they get? How many can you find in a window of a certain length? Questions like this, right? So with a view to this, you might consider the following sort of average, where you take sum of f and this difference here, and this is just, I'm just normalizing by the average gap between zeros here. So now these guys have average gap 1, but you can forget about it. Okay. And like I said, we want to look at like local properties. So we're going to take f to be fairly concentrated around 0. You know, maybe you'll take as a characteristic function of some certain interval or something. Okay, but for the moment we can just take smooth, nice guys, whatever. Okay. So first thing to do is you might want to separate these variables here, and so you can unfold f as the inverse Fourier transform, and then push this sum through, and then yes, you get a double sum here that's now separable. But there's a couple of issues with it. It's quite erratic. So number one, there's quite a sharp cutoff here, and you have some oscillating guys here, so your error term is probably going to be quite large, a bit unwieldy. Another issue is that, well, let's say you wanted to compute sum over zeros, the natural thing to do is apply the explicit formula, right, and get it in terms of primes. Well, when you do that, you're going to have a Dirichlet polynomial of primes over primes that has like a pointwise dependence on big T and alpha here. So you translate your problem about an oscillating sum into some other oscillating sum that's like, you know, all is equally intractable. So Montgomery's idea, it's a really nice idea, that you can solve both of these problems at the same time. And the idea is that you introduce some smoothing into the initial problem. And so the smoothing will smooth your sum, obviously. And it can also introduce some extra averaging. So you solve this problem of the pointwise dependence on T and alpha. Okay. So what you do is we introduce this weight here, where it's given explicitly as this. So since f is going to be concentrated, more concentrated than w, we can introduce this weight here without much of an issue, right? Okay, then when you do the same thing as before, unfold the inverse Fourier transform, we now get this sum here. And as mentioned, this is much nicer now because we have some extra averaging, and the sum over zeros that we get has some much smoother behavior here. Okay. So this formula is not too hard to prove. First, you can just restrict your sum over zeros to between 0 and t, like on the left, due to this localizing factor here. And then for the same reasons, you can extend this integral here over the whole real line, and then you just expand the square and integrate, and get just apply this formula here. You get this on the left. Okay. So these dots here just represent the error terms from these truncations and extensions and stuff. Okay. So now we're in like a better position. We have some averaging and we have a smoother guy. So now we can try and apply this explicit formula. And what you do is when you apply the explicit formula, you get something of the following shape. So we get our sum of primes here in terms of a Dirichlet polynomial. You get a term here that is essentially the expected value of this guy here. And you get another term here. This is essentially reflecting the fact that when y equals 1, say, you have no oscillation, right? And then this sum is just localized to a window of length 1 approximately around t. And in such a window, there is log t zeros. So that's why you have a log t here. Okay. But of course, the main guy of interest is this Dirichlet polynomial here. And so when we want to compute the mean square, we can just, well, we can do that. We can just apply this Montgomery-Vaughan mean value theorem, right? So when you do that, you get this guy here. And so in particular, if y is little o of t, we get the asymptotic formula. And then you can compute this guy just with the prime number theorem. And so if y is little o of t, then you get this asymptotic here. Now, so on the previous slide, we had y is t to the alpha. So this condition here translates to alpha between 0 and 1. Okay. And of course, these other terms here are pretty easy to compute. Okay. So in this way, Montgomery showed that you can, for alpha between 0 and 1, you can understand this guy, this sum here. And I just normalize, you just normalize by the number of zeros on this interval. Okay. So for negative alpha, you can just use the fact that f is even. This follows just from these types of equalities here. Okay. Okay. So if you return to the original problem where you had this sum of f over these differences of zeros, unfold the guy again. This guy is just coming from the normalization here. And then I can get an integral in terms of this big F of alpha here. And as we just seen, so if alpha is of modulus less than 1, then I can understand this guy pretty much asymptotically. And so in particular, if the support of my function that I started with is contained in this interval here, then I can pretty much understand this sum completely. Okay. Okay, but of course, so we want to look at, let's say we want to look at really local properties of zeros, then the more local you want to look, the more concentrated you want to take f. But of course, the more concentrated you take f, the wider f hat gets, right? So it's of interest, like, to extend our understanding of f, big F, outside this range here, right? But of course, to do that, then we're going to need to understand mean values of longer Dirichlet polynomials. The condition alpha less than 1 translated to a short guy. Okay. So if we want to understand the long guys, then we need to input this conjecture here, and this is what Montgomery did. So he showed that assuming this Hardy-Littlewood conjecture here, that when alpha is bigger than 1, actually the behavior changes a little bit, and f of alpha, instead of going alpha, It just becomes 1. And essentially what happens is this expected value term here cancels the main contribution from this, and you're just left with 1 in the end. Okay. Now, there's no reason to suspect that this might change for larger alpha. Also, you might expect the same type of behavior with the error terms as we had with or as we expect for the divisor function, which is to say, when you do the off-diagonal calculations, when this error term, when averaged over h, behaves much better. And in that case, you would be able to extend to alpha larger than this as well, alpha bigger than 2. Okay, so with these sort of considerations in mind, Montgomery conjectured that f of alpha is asymptotic to 1 for all alpha bigger than 1. Okay, well, if you have an understanding of f in such a range, then you can understand pretty much any sum over zeros that you want. So there's a couple of, well, more than a couple, there's quite a few nice consequences of this conjecture. So the first one is this famous connection you get with random matrix theory. So you can approximate the characteristic function of an interval here. And what you get when you do this is the following integral on the right-hand side. And this pair correlation function here is exactly the same as the pair correlation function for eigenvalues of a random unitary matrix, chosen with the natural sort of Haar measure. So this is really interesting connection with random matrix theory here. And since this integrand here is positive, you immediately get some nice consequence. In particular, the average gap between consecutive zeros, gamma plus here is just the guy after gamma. So these gaps can get arbitrarily small. And in a sort of quantitative form, it doesn't need to be quite as strong as this, but in a quantitative form, this fact here implies that there are no Siegel zeros either, which I think was Montgomery's original motivation for looking at this. I think, I'm not sure. Okay. And finally, another nice consequence of Montgomery's conjecture is that almost all zeros are simple. So you get 100%. Okay. So that's zeros. And in principle, you can get some really nice consequences about zeros just from understanding long Dirichlet polynomials in theory. I also want to talk about not just zeros, but also about fluctuations of the zeta function on the half-line, sort of related problem. So typical fluctuations and more extreme values. And in this case, you have Selberg's central limit theorem. So this is telling us that the log of zeta is approximately Gaussian with mean 0 and variance half double log t here. So in particular, the zeta function typically is around this size here. But of course it can get larger. And so the thing to note here is that this result is for fixed v with respect to t. Now, let's say you wanted to look at some more extreme values than these typical ones. Well, then you might look at the moments here. And for a given 2kth moment, we know that the main contribution to this guy comes from values of this size here, which is quite a bit larger than the typical guy, right? So in particular, if you want to understand moments, it's of interest to extend this central limit theorem to a large V range. Right? Okay, and this is what Sound did conditionally on the Riemann hypothesis. So he showed that you have these Gaussian bounds extend into the sort of large deviations range for V up to this size here. And this covers this covers the range for any fixed moment. And it allowed him to show that you have near sharp bounds for the moments here. Now, the zeta function can get much larger than log t to the k, of course. So it's conjectured that you have something of this size here. And so this range here is, we're only really just getting into the tails. I mean, and you can show that actually there's large values of the zeta function that are nearly of this size here. And so then really we're talking about v of size square root log t and not square root double log t, right? So there's quite a bit to go, and it's not clear if this Gaussian behavior extends into the range here or what. So yeah, so it's of interest definitely to extend these large deviation results. Okay. So let me just talk briefly. Let me talk briefly about the proof of this central limit theorem and these large deviation stuff. So, of course, it's analytic number theory, so we just have to prove these sort of distributional results by moments. We don't have much access to any other things, really. And so if we want to look at the moments of log of zeta, we need some approximate formula. And this is a more explicit version of the explicit formula that I mentioned at the start. So here you have this sum over primes, and here's the contribution from zeros here. And if just for the minute we assume RH, then we can examine this guy a little bit here. So on RH, this guy here is less than 1. Okay, so that's all good. Also note that we're going to be integrating with respect to t, and on the left we have a log of zeta here, and so these singularities here are logarithmic, of course, and hence integrable with respect to t. Now, this function here is essentially localizing the zeros, this sum over zeros, to within a small window of length 1 over log x around t. So of course you have this factor here, which provides some localization. Also, you have something that's oscillating in the numerator here. So we expect that if you're away from t outside of this window of length 1 over log x, then this guy should be small, at least on average. Okay. And within the window, so in a window of length 1 over log x, on average you have log t over log x terms. So on average, you can expect this guy to be sort of behaving like log t over log x. Okay, but this is nice, right? Because now we have a formula in terms of just a Dirichlet polynomial, and we can just plug in x is some small power of t and hope to compute the moments. Okay, so let's say you wanted to compute a 2kth moment. Well, then you need your guy to be short. This polynomial here to be short, so you take x is t to the 1 over k. Okay. So then you have a short guy here, and he's short, so it's just diagonals that contribute, off diagonals that contribute anything, asymptotically. And then, so with this diagonal sum here, the main contribution just comes from pairing up the primes like this, which there's k factorial ways to do. And each time you do it, you get a sum of this form here, k copies of that. Okay, so here's the variance. And of course, we have some k factorial, so complex Gaussian moments, right? Okay. So sort of moreover, this is telling you morally why you should have a central limit theorem, right? So first of all, you can approximate zeta by some sum that is short, and when it's short, you have essentially pure orthogonality, and hence, in that sense, you can look at the p to the it as just independent random variables. And so we have a sum of independent random variables, hence central limit theorem, right? Now, for large deviations, of course, you want to take large moments, k, depending on t. and then just apply Chebyshev's there. So this is the principle of sounds upper bound. But if we want to extend these large deviation bounds further into the tails, well, when you take larger moments, this error term here is blowing up. This was a log t over log x. And so with this choice here, it's of size k, right? So you get a k to the 2k. So you get some blow up, right? So what would be nice if we want to compute more large deviations is that if you you can compute higher moments, but without taking such a short guy, right? And then there would be no blow up of this error here. But of course, if you have a guy that's not so short, you need to understand the mean values of these long Dirichlet polynomials, right? And of course, for that, you need access to this Hardy-Littlewood K2 plus conjecture, which we don't have. Okay. So yeah, so I want to talk about some sort of examples, some special cases where you can actually compute these types of sums for longer guys, if you assume RH, and you don't need to assume this these twin prime conjectures, but okay, you do need to assume RH, which is still a pretty big conjecture. Another aspect is that you need to your Dirichlet polynomials need to have some weights, and this makes the arguments a lot smoother. I'm not sure really how crucial these weights are, but anyway. Okay, so the weights that we're going to take have some properties I list here. Essentially, what you need is some guy that has a nice Mellin transform, which gives you absolutely convergent integrals here. And also you need some sort of, I don't know what you call it, a concentration property or something, where after this transformation here, you get something that's again going to give you absolutely convergent integrals and no blow-ups or anything. So fairly concentrated around s equals 0. Okay, so these are sort of the general weights, but you can just keep in mind some like a Fayet kernel type guy, right? So in this case, you have the Mellin transform looks like this. And so we have this absolute convergence, and you can check after this type of transformation, you have these types of bounds here. So unfortunately, these weights don't cover the basic sharp cutoff, because this Mellin transform here doesn't give you absolutely convergent integrals, unfortunately. Okay. So with these weights and assuming RH, then we get the following. So for x less than t to the 4, so the 2kth moment is given by this expected Gaussian guy here. And you can also do either the real or the imaginary parts, and you get the expected sort of Gaussian moment coefficients here too. Okay. So just a few remarks. First of all, these sums are of size approximately double log t. So this is indeed an error term. And in fact, you can take k large to some certain point, about like triple log over quadruple log or something, and this still holds as an asymptotic. Now, we're not going to prove this in the usual way where you have diagonals and off diagonals, but if you did, what this is saying is, notice that this is a pure diagonal sum here. There's no constant c. This is just purely diagonals. And so what this is saying is that on RH, off diagonals do not contribute to these types of mean values here. Okay. And furthermore, like if you were to do this sort of off diagonal calculations, that you must have some cancellation of these error terms when you average over H that we've been talking about too. Okay. Okay, so let me just briefly go over the proof. So the rough idea is that, well, yeah, okay, so this provides like a rough basis for the proof. So recall that on average you have this, this formula in terms of primes. And this error term that we had log t over log x, well, is quite stable on when you change x from, say, t to, you know, t squared or something. It's so you might hope that this error term here is kind of insensitive to whether the Dirichlet polynomial is long or not. Right? I mean, if that's the case, then you can take some short guy of this size here and then just compare this formula at x and y here. And in that case, you get that, at least on average, because this is instead on average, this formula here, you get that on average, you can replace your longer guy with a shorter guy. So that's sort of the underlying idea or principle that's happening. But in practice, it's quite difficult to deal with this term here, because it's in terms of zeros. What we can do is express things in terms of contour integrals, shift close to the half line, but not past it, so that you don't have to pick up any zeros. And then you can just deal with the contour integral itself. And at some point, we're going to input a short Dirichlet polynomial for our long guy. So the principle kind of remains the same, but we just use contour integrals instead of explicit formulas. Okay. So for a proof sketch, I'll just do it with this basic Fayet kernel here. And I'll note that we can accept errors of some bounded size throughout. So we're going to be integrating with respect to t, so a bounded error would just give you big O of t. And we're after something of size t times some power of double log. Okay, so that's why, essentially why they're accepted. Okay, so let's do this contour integration first. So first thing is you just express this in terms of its Mellin integral. So you have the Mellin transform here and the Dirichlet series for the Dirichlet polynomial here. There's some prime powers as well that I'm missing here, but of course, as usual, they don't really matter. Okay. So now, as I mentioned, you want to shift close to the half line. So you shift this contour to the left, and you, in the process, you pick up a pole s equals half minus it, and this contributes something of size x to the half over t squared from this decay here. Okay, so this is where the condition x has to be less than t to the 4 comes in. Is that this, in that case, this error term is big O of 1. Okay, and we can essentially ignore this contribution from the pole. Okay, so now we're close to the half line. You can truncate the integral at some low height, say plus minus I. The log of zeta is less than log t, and we've got a factor of log x out front, 1 over log x. Also, my integrals with this choice of weights are nice, as I mentioned, so this truncation doesn't incur any reasonably sized errors. Okay, so what's the point of all these manipulations? Well, okay, so after tidying up and a couple of substitutions, you get something like this. And essentially, here's the point where we want to input the short Dirichlet polynomial. So when we take the 2kth moment of this, expand things, and integrate with respect to t, well, we can replace the log of zeta by a short Dirichlet polynomial on average. So that's where we input these things. And when you do this, you get some errors of size O of 1. But you'll notice that the integral here is very nice, right? Absolutely convergent, no blow-ups near 0, things like that. This is all afforded by these nice weights. So essentially, we have like a really sort of efficient representation of our Dirichlet polynomial here. And then we can carry out this strategy. Okie doke. So raising this guy to the 2kth power, absolute values, and integrating with respect to t, well, when you push the integral through t through, you see that you need to understand these sort of correlation integrals here. And here, y is some small shift, less than 1. So, okay. And as I mentioned, this is where you just input the fact that zeta is a short Dirichlet polynomial on average. And so we can compute this guy asymptotically with good errors. So when you plug this guy in here, you just, again, we got a short guy, so you just take diagonals. And in that case, we have essentially the same as before, just this diagonal sum, except now we have these small shifts here. But you'll notice that, so we have a lot of y integrals outside. We have 2k y integrals outside, right? But everything's separable now, so it's easily computed. So then you can compute the integrals over y, and you get the result after sort of doing sort of inverse Mellin transforms, essentially. Okay. So yeah, just a small remark. You can see that this smoothing is really helpful, right? We have absolutely convergent integrals, no blowups. If you tried with this brutal cutoff and its transform here, you'd have, first of all, difficulty truncating the integral. That might be doable. It's not too important. But more importantly, when you apply this approximation for zeta, this error, you have this error O of 1 here. That would lead to a blow up here in this case, right? You'd get a double log x, and that's the target bound that we're after, right? So it would completely ruin it. Okay, so that's one of the reasons you need these, well, one of the reasons these weights make things much simpler. Okay. So, unfortunately, this doesn't give any new results for log of zeta, and it's might be fairly clear why, because we haven't actually inputted any new information about zeta, right? We've just used the fact that it's given by a short Dirichlet polynomial on average, which is exactly the same input as used before, right? So, unfortunately, this doesn't give any new results for zeta in that sense. But nevertheless, you can get large deviations for the polynomial itself, which are new. As it stands, though, you have this, so you have this asymptotic formula, and the error term was of this size here. And of course, this k to the 5k here is not so good, it's not so useful for large deviations. You could probably improve it, but what you can do is you can do a slightly more efficient way of getting large deviations. And that's essentially applying an argument of sound. So what we want to input is an upper bound of this shape here in a more direct way, and then analyze each of these components separately. This is how sound does his upper bound for large deviations of zeta. Okay. So then it's helpful for a start if you can just modify your weight to have positive transform here. And I'm just doing this for Mellin transforms. You can, but of course, if you work with Fourier transform, it's clear that the transform of this guy is just the sinc squared guy. So, okay, it's not too important. So you do the same as before, right? You get this efficient representation, and now you can shift to the line real part of s equals 0, and you get this sinc squared guy here. And this is positive now. So we can upper bound this, after taking real parts, we can upper bound this and apply sounds bound here. So here, obviously, it's important that you have a positive kernel so that you don't lose the upper bound, sorry. But then you can essentially apply the same argument as sound and just analyze these components individually. The only difference really to sound's argument is that you have an extra integral over y, but you can just deal with that with Holder's inequality. And because it's like such an efficient sort of nice integral, you don't lose anything, you know. Okie doke. So with that, you get the following large deviation bounds for these types of sums here. So you get this term here, like the expected Gaussian, and then this other term here that starts to dominate when you're sort of a bit further out into the tails here. So I'll briefly just mention. So yeah, we have these Gaussian bounds, and it's up to polynomials of such a length here. Previously, for these types of bounds, you needed something quite a bit smaller. Also, if you're looking at like the full range of V, I mean, this guy can go up to size, what, like log t, or conjecturally like square root log t or something like that. And if you want something in the full range of V all the way up to these maxima, then this was something with some decay of this size was only previously available for x like really small. Okay. What am I saying here? Restricted to positive. Yeah. Okay. Never mind. So I'll just finish just with consideration of other Dirichlet polynomials. So you can try and apply the same sort of argument to other guys. And so, for example, you can consider a guy that instead of approximating log of zeta approximates this logarithmic derivative here. So you have a weight log p now. And you might expect, well, a weight log p doesn't make that much difference, but it turns out it does. So there's a few reasons for that I'll get into in a sec. Number one, it limits you to the mean square, which we expect to be of this size here. And without the weight log p, as you saw, there was no contribution from the off diagonals. When you have the weight log p, you start to get something that looks like an off diagonal contribution. So you get something more precisely, you get something that looks like this. So again, assume RH and take this weight here. Then you get something that looks like a purely diagonal guy. Plus you get this term involving this Montgomery's function f of alpha from earlier. And this is something that's suggesting a contribution from off diagonals here. Okay. Okay. So notice that this range of integration is bigger than 1, where we don't really know f of alpha. If you assume Montgomery's conjecture here, then you get an asymptotic of the expected size. But of course, Montgomery got this conjecture here from applying this Hardy-Littlewood K2 plus conjecture anyway. And assuming that, you could probably compute this guy asymptotically, right? So it's not really giving you new information. However, without this sort of conjecture, you can use results that tell you about f of alpha on average, so that it's at least bounded on average. And this allows you to give the order of log t squared. Okay. So briefly, just a few comments on the proof, why it's different when you have a weight log p. So you do the same as before, except now you will have a logarithmic derivative, and then so integrating by parts, you get your log of zeta, but now you get a derivative here. And this derivative adds an extra factor of log x, right? And we're looking for asymptotic of size log t squared. So so now you need to be really careful, right? Because if you ever apply some error term that's bigger of 1, you'll get log x, and then after squaring, you'll get log x squared. And so you're going to lose your asymptotic. So I mentioned that here, you know, this would not be sufficient, this type of approximation here. So you can do the same sort of process, and then you see what you need is like really precise estimates for these correlation integrals here, down to the level of little o of t. Okay. So you can simplify things slightly. Just an extra contour integral argument allows you to reduce this just to the study of the imaginary part of the log is commonly notated as S of t. And for this, you can, to understand this guy, you can apply results of Goldston and Fuji, which gave like, so Goldston gave really precise bounds for this down to the level of little o of t, which is what we need. And his constant terms involve this function f of alpha, and that's why it pops up in this mean value too. Okay, so using Goldston's arguments and arguments of Fuji, then you can get very precise estimates for our correlation integral here, and that's sufficient to sort of finish the argument and give the result. And I think I will stop there. Yep. Thank you.
Thank you.
Thank you, Winston, for the nice talk. And we have time for questions. Does anyone has a question?
So I'll ask a question. Wait, hi, Winston. I had a question about like the Dirichlet polynomial, like when you like the how do I put this? The loss deviations for the for the Dirichlet polynomial approximation of log zeta. How does that vary from, like, how do you expect that to behave relative to, say, the loss deviations of log zeta itself? Like, for example, like the loss deviations of log zeta have like this ck that comes from the moments factor in it, right? Like that's the expectation.
What am I looking? Large deviations of zeta, sorry.
Yeah, so the question is, you're proving this large deviation result for these polynomials, right?
Yeah.
But for the large deviation of zeta, you expect, like, for the larger k to have some what's it called, like a constant, in the thing that comes from the higher moments of zeta, right? Like there's that paper of Radzivi where he looks at
right, yeah. As in,
so
like, okay, this guy, yeah, it will change when v gets bigger than this.
exactly, yeah. So my question was, like, is this some similar phenomena for the for just like the polynomial approximation instead of log zeta, or do you expect it to be Gaussian for a larger range?
Right. Yeah. Yeah. I don't know. I would expect the same as for zeta, which is essentially Gaussian guys. But yeah, in terms of an asymptotic, actually, I'm not sure. Yeah, might be worth a thought. Yeah.
Thanks.
More questions?
So maybe I have one. So you look at these Dirichlet polynomials, and you think of them as approximations to log of zeta. Is that how you think of them? And if so, how do you know how much further you'd have to go? Like, how much larger would they have to be to capture log zeta, or it's not the game that you play?
Well, they can capture them for quite short guys already.
Yeah, true. But you said.
Yeah. Yeah. So in principle, if the longer guy that you could take, the smaller this error would become, and so there wouldn't be as many blowups. That, I think that in principle still remains true. But the proof that I used to compute the moments of this guy, it just inputs like another short guy as well. So you kind of lose there's no new information, right? I mean, it comes in the error terms here, like you have something that's really large in terms of k, so it doesn't give you anything new, unfortunately.
So
Okay.
that means that there will be no gain, like they will give no more understanding on log zeta if you could prove this for larger x, right?
Yeah, not at the moment. I didn't find any applications yet.
Okay. Okay, so one probably has to do something smarter with the thing that's considered the error term, right? Have to understand oscillation of that too.
Yes, yeah.
Okay.
Yeah.
Hi, Wayne. I forgot the definition of this function phi of x of p of prime p. It's
You can just think of this guy here.
okay. So it's like a Arias mean, right?
Yeah, it's like a not quite, because you have the Rees mean would be like x over x, well, little x over big X. This is log x over log x. So yeah, it's more like a slightly smoother guy. But I guess I'm not sure Rees mean would work. You get this for sure. You get this nice behavior, absolutely convergent guys. But you don't have this one, unfortunately, for Rees means.
I see. More questions?
Or maybe one more question. This is not on the archive yet, is it?
Yeah.
Oh, it is? Okay.
Yeah.
Okay, cool. I'll look it up. Thanks.
What was the question? I didn't
Oh, I was
hear.
just asking whether this was on the archive already.
Okay. Okay, very nice. Thank you very
just
much,
wait.
Winston.
Maybe just one other question. Is this, do you have hope, or is it, I never know if my question makes sense, but to push the results, the one with the log that you said you only had the second moment, and I guess, is there a point in trying to get, can you go higher, like?
Higher moment.
Yes.
Yeah, maybe. I'm not.
What would it require?
What would you'd need? So you'd need the sort of fourth order correlation, whatever, for this type of guy here. So you need to understand that. Yeah, essentially a fourth shifted moment of log zeta, but again, I guess down to quite a precise level, which I think might be out of reach. But yeah, be interesting to look at.
And so how did you do it? How did you get the information that you needed from this integral?
From this guy?
Yeah.
Here you just apply some results of Goldston. It has really precise formula for this down to the level of t. And you can just sort of modify the argument to get the shifted version.
Okay.
Yeah. But that type of, so Goldston type of result doesn't exist at the moment for the fourth power. Which is,
sure. Okay. So how good? Sorry, I mean, not my promise. My last question. How good is the development that he shows? Oh.
What, for this integral?
Yes.
So Selberg had t double t plus big O of t on RH. He gets the constant term and then little o of t.
Okay.
And I think with more conjectures, you can show the little o of t is like t over log t or something, if I'm not mistaken.
Okay.
Don't quote me on that. Yeah.
Oh, sure.
Yeah. So you get quite precise. Yeah.
Okay. And okay. All right, cool. Thank you.
Okay, so thank you, Winston. Thank you, everyone, for coming. Next week, there is Alexander Manjiro.
Yeah,
See
from
you.
Durham. Yeah. Yeah, just a quick poll. If did anyone didn't? I mean, if you haven't received the email or the reminder, like, please let us know. You can just tell us on chat. Yeah, we were still trying things. Sometimes our mails seem to get locked. But, yeah, I mean, thanks for coming.